Hi guys, welcome back to YouTube channel Chemistry Live UGPG. Today we are going to talk about carboxylic acids and its derivatives, lecture 4. So this will be highly beneficial for BSc chemistry students under CBCS syllabus. So I have a simple message for you guys. Please think for innovation, be creative, learn everywhere, anytime and help to learn others. So this is the syllabus under Unit 4, CC6 paper, Semester 3, carboxylic acids and their derivatives. So today we are going to talk about preparation and reactions of acid chlorides, acid anhydrides, esters, amides and comparative study of nucleophilic substitution reaction at acyl group. So this is the prerequisite knowledge that we need. We know that reactant is converted to product in the presence of a reagent. But we need to know how that reactant is converted to the product. So that is called the mechanism. What is mechanism? So mechanism shows the movement of double-headed arrow. So that means the movement of both the electrons, how the bonds are broken and new bonds are formed leading to formation of product, which may be multi-step process or one-step process. So this is the bond, AX bond. So this bond is broken here heterolytically. So the atom on which this bond is breaking, that gets negative charge with both the electrons, that is known as nucleophile. And other one is positively charged, so that is electrophile. And in principle of mechanism, always the nucleophile will attack to the electrophile. So as a result, you get the nucleophile-electrophile bond. And in other words, we can say, and when this bond is broken, so you generate again nucleophile and electrophile respectively. So now we will talk about preparation and reactions of acid chlorides, acid anhydrides, esters and amides. So this is the carboxylic acid. So if we replace this hydroxyl group by a X, that is Cl, so that becomes acid chloride. If we replace hydroxyl group with OCOR, that becomes acid anhydride. If we replace hydrogen of carboxylic acid by R, that becomes ester. Similarly, if we replace this OH group by NH2, that becomes amide. Now next is preparation of acid chlorides. So you react the carboxylic acid with thionyl chloride, it gives acid chloride. Similarly, you react the acid with the PCl5, phosphorus pentachloride, you get acid chloride. Then reaction. Acid chloride RCOCl react with water, giving rise to carboxylic acid. Similarly, acid chloride react with ammonia, giving rise to amide. Similarly, acid chloride can react with benzene in presence of Lewis acid, aluminum chloride, giving rise to Friedel-Crafts reaction. So that is a ketone. Similarly, now next is acid anhydride preparation. So if you react thionyl chloride with sodium salt of a carboxylic acid, 2 equivalent, you get acid anhydride. Similarly, if you take 2 equivalent of carboxylic acid and you heat it with phosphorus pentoxide, you get acid anhydride. Then reaction of acid anhydride. Acid anhydride can react with HCl, giving rise to acetyl chloride and acetic acid. Similarly, acid anhydride can react with PCl5, giving rise to acetyl chloride and phosphorus oxychloride, POCl3. Then acid amides. You start with acid chloride, you react with ammonia, giving rise to acid amide. Similarly, ammonium salt of carboxylic acid upon heating, giving rise to acid amide. Then acid amide react upon reaction with P2O5, giving rise to alkyl cyanide. Similarly, acid amide react with bromine and potassium hydroxide, giving rise to primary amine RNH2. This is known as Huffman-bromamide reaction. The next is esters. So acid react with ROH, alcohol, giving rise to ester. Then acid also react with diazomethane, CH2N2, giving rise to ester. Then reaction. Ester reacts with ammonia, giving rise to amide and alcohol. Similarly, ester can react with bromine and red phosphorus. You can get the bromo derivative. Similarly, esters can be reduced with lithium aluminum hydride, giving rise to alcohol. The next is nucleophilic substitution at acyl group. So what is acyl group? We should know. So this RCO group is known as acyl group, or CH3CO group is known as acyl group. So these acid derivatives or acyl compounds can be represented in general as RCOZ, where Z is Cl, OCOR, OR, NH2, where R is alkyl group. So the group Z can be replaced by some other basic group or nucleophile Nu minus. So here the nucleophile or basic group lone pair can attack as nucleophile, so it will attack to carbonyl carbon, and this CO double bond will break on oxygen. So it becomes O minus. When this O minus will come back, it will kick out Z as Z minus. So as a result, you get this nucleophile substituted at this acyl group. So this reaction involves the substitution at the acyl group. It is called nucleophilic acyl substitution. So this is the mechanism. So this nucleophile lone pair of electron will attack this carbonyl carbon, and this CO double bond will break on oxygen. So it becomes O minus, and the nucleophile will be attached to this carbon. So you get this transition state, which is a tetrahedral structure. And this is the anionic intermediate. So when this O minus will come back, it will kick out Z as Z minus. So this is the substituted product RCONU plus Z minus. And this can be taken place in presence of acid. So in presence of acid H plus, so carbonyl oxygen lone pair act as nucleophile, it will attack to the electrophile H plus. So you get this protonated form of OH plus, and nucleophile will attack this carbonyl carbon, and this double bond will break on O plus. So as a result, you will end up with this tetrahedral intermediate. When this OH bond will break here, it will kick out Z as Z minus. So as a result, again you get the substitution product plus ZH. Next is comparative study of nucleophilic substitution at acyl group. So nucleophilic acyl substitution versus nucleophilic alkyl substitution. So this RCOZ is more reactive than RZ, where Z equal to Cl, NH2, OR, etc. So we already know the nucleophilic substitution reaction like SN2. So nucleophile attack from backside. So as a result, you will get this pentavalent transition state, which is unstable, and ultimately nucleophile will be attached to this carbon center, and the stereochemistry is reversed plus Z minus. So here a strong sigma bond has to break before a nucleophile attaches to the alkyl carbon. Similarly, the nucleophilic acyl substitution, we already know the nucleophile will attack to this carbonyl carbon, and this CO will break on oxygen. So you get this transition state tetrahedral structure, and when this O minus will come back, it will kick out Z as Z minus. So this is the anionic intermediate tetrahedral carbon. It is more stable. So as a result, you get nucleophilic acyl substituted product RCONU plus Z minus. So the carbonyl group in acyl group is unsaturated. The attachment of the nucleophile at the acyl carbon requires the breaking of only weaker pi bond and places negative charge on oxygen. That is a good acceptor of electrons. The nucleophilic attack on trigonal acyl carbon involves a stable tetrahedral intermediate. So hence the nucleophilic attack on trigonal acyl compound is more favored over tetrahedral alkyl substitution. So please subscribe to our channel Chemistry Live UGPG. So this is also available in the website www.chemistryliveugpg.com. So this is the channel Foundation Chemistry AB for class 11th and 12th students. This is also available in the website www.foundationchemistryab.com. So this is a simple step towards e-learning, making life better. Thank you all for learning.